Okay, we are now on to lesson 5, which is all about related rates. And this tends to be the lesson that everybody absolutely hates. So I'm just going to try and explain it as best as I can to you, but it is a weird thing to grasp. So I'll just try my best. So the thing with related rates is you're given some information about a scenario, typically with a rate, and you're asked to find a rate, usually. And the thing that's so hard about it is that it's always going to be word problems, and you're going to have to create your own variables for stuff. So to start, what we're going to do is we have some basic situations. We're not actually asked to find anything here, but I'm just going to show you how to actually write rates based off wording. So the important thing before I actually start with related rates is everything. Everything is going to be with respect to time. So remember last video with implicit differentiation, it was always with respect to x, and you could tell what you're deriving with respect with based off the second letter in the denominator. But so we only talked about what it's with respect to. We never talked about what we're actually deriving. So in related rates, this letter in the top is going to always pretty much be different. In our case, last video with implicit differentiation, we had dy dx, which means differentiate y with respect to x. But here with related rates, there's going to be a few different things. One, it's going to be with respect to t. So t is always going to be our second letter in the denominator. And the thing we differentiate with respect with, that's going to change problem to problem, and it's going to be different all throughout the problem because you're typically going to have multiple rates. So let's start to try and write some rates based off these 4 situations. So the first situation is John is growing at a rate of 3 inches per year. So John is growing. And so what's a variable we can give to the fact that someone's growing? And the thing I would first think of is height, because their height is increasing. So we're going to do dh dt, letting h be height, to show that it's a rate of change of height. And what does it say? It's a rate of 3 inches per year. So dh dt, which is the rate of change of his height, is going to equal 3. And then if we wanted the units, we could also say that inches per year. But all we really need to know for right now is that dh dt is equal to 3. Now, if we were to work on our next situation here, where it says the population is shrinking by 5 people per day. So first we need a variable, and so it's about the population, so I would probably choose p. So dp dt, and they say that it is shrinking by 5 people per day. So dp dt equals 5. But because the population is shrinking, is actually going to equal negative 5. Now for the next one, the oil spill is increasing by 4 feet per hour. And this one, I can't really think of a good variable, like that something fits with this. So when you can't really think of a variable, just choose something simple. Like, so in this case, I would probably choose dA dt. It's just first letter of the alphabet, and there's nothing really significant in the problem to give us like a letter. So dA dt, and that would equal, it says the spill is increasing by 4 feet per hour. So dA dt would equal 4. And lastly, we have water is draining from the tank at 2 inches per second, 2 cubic inches per second. So we have a W here, W for water, that would probably be our variable. So we would write dW dt, and that is equal, it says 2 inches per second. But notice it says water is draining from the tank. So water is decreasing, and that means water is going to be negative 2. So 2 things to keep in mind when we're working with related rates and writing our actual like rate of change and all that stuff, our rates. So first is to actually identify what's a rate and what's just a value in an equation. If you could see something changing, that means it's going to be the rate. So water is draining, or the spill is increasing, or the population is shrinking, or John is growing. So pretty much it's going to be, if it says ing, I think that's basically what it's going to mean. That's your rate of change, or one of your rates of change in your related rates. And now also another thing is that you probably don't want to choose any letter of the alphabet for your variables. So what maybe I had ds dt, and over time, like, well, when we have ds dt, you'll see in a few minutes when I actually give some related rates examples, you don't just use the rate ds dt, you also use the actual variable s, and s's can change to 5s throughout a problem through bad handwriting, and that just causes a bunch of confusion that makes you get the answer wrong. So S is a bad variable to choose, and for some people they say Z is a bad variable to choose because Z looks a lot like 2, and that's true, but a good way to get around this is draw your line through a Z like that, and that way if you have a line through it, you know it's a Z and not a 2. Okay, so this is our first example of a related rates problem, and then so a brief overview of how the rest of the video is going to go. So there's like 4 kinds of related rates. There are geometric formulas, there's things called shadow problems, there's Pythagorean theorem problems, and trig problems. So I'm going to give you like 1 or 2 examples of each of those, explaining how they all work, and we're just going to go from there. So this is our first one, and as you can see, it's kind of scary, just a really long word problem, but that's really all related rates is, so let's just hop right into it, see if we could find any important information. So it says that at a sand and gravel plant, sand is falling off a conveyor and onto a conic pile such that the height of the pile is changing at a rate of 0.045 feet per minute. The diameter of the base of the cone is approximately 3 times the altitude, and so with this information, we'll find the rate of change of volume when the pile is 12 feet high, and we're given a formula for the volume of cone. So that was a lot of information, so let's go back quickly and let's highlight the important things that we need to know. So we're skimming through this. It says that the sand and gravel, whatever, is falling onto a conic pile. So an important thing you should do with related rates when you're reading is you should try and draw a picture of what's happening. So it says we have a conic pile of sand and gravel. So it's going to look something like this. Because like the sand falls on top of it, that's how it makes the cone. Reading on more, it says that the height of the pile is changing at a rate of 0.045 feet per minute. So the height is changing at a rate of this. So we see changing, so it just basically tells us that's the rate of change and it says it's of the height. So typically in problems like this, when we're talking about height, we give it the variable h, and it says it's the rate of change of h. So we're going to write dh dt, and that is going to be equal to 0.045. Continuing on, it says that the diameter of the base of the cone is approximately 3 times the altitude. And for our purposes, the altitude basically just means the height of the cone. So from that, we could write the equation d for diameter is equal to 3h. And this formula does not have d in it, but it does have r. And remember, diameter is 2 times the radius, or r. So we could say 2r equals 3h, or r equals 3 over 2h. So keeping this in mind. Continuing on, it says, at what rate is the volume changing? At what rate is the volume changing? So they want us to find the rate of change of the volume with this problem. So they want us to find dv dt, because that's the rate of change of volume. And then what other information? They say when the pile is 12 feet high. So find this when h equals 12. So at this point, this is when we actually start to solve the related rate problem. And to solve a related rate problem, what we have to do is we use a formula, either one that's provided to us or one that we come up with based off the actual stuff they tell us, whatever, and we derive that formula. Then we can just plug in values and then go from there. The only issue is that typically happens with cone problems. So we said we want to differentiate, so our formula is 1/3, or v equals 1/3 pi r squared h. But notice, we're going to have to derive this. It's going to be some product rule, a bunch of ugly stuff. But by implicit differentiation, if we derive r squared, that's going to give us 2r dr dt. So we're going to have this somewhere in our answer because we're deriving that r. And the issue is we have to plug in values for every other variable that's not what we're solving for, and we're solving for dv dt. So that means we're going to have to plug in a value for r and for dr dt. We don't have a value for dr dt, so that's not going to work for us. But there is a solution to this. The thing we have to do is make a custom formula for a cone specific to this cone that we have. And the way we do that is use this piece of information where they say the diameter is 3 times the height, and we change that by solving for it. It means that the radius is 3 over 2 times height. So using this, we could just plug r equals 3 over 2h into this general volume equation. So if we do that, we get v equals 1/3 pi, and then instead of r squared, we're going to have 3 over 2h all squared multiplied by h. And if we simplify that a little bit, we are going to get v equals, we could turn 1/3 pi into pi over 3 times 3 over 2 all squared times h cubed, because h squared and then h. We could simplify this 3 over 2 squared thing, but related rates are pretty much always calculator active, so we just throw it into the calculator at the end. We don't have to worry about it. And now there is no r in the equation, so when we differentiate this, we will have all the values that we need to plug in. So I'm just going to clean up the board a little bit, and then we'll move on from there. All right, now we have everything cleaned up. We have our equation for volume of a cone. V equals all this stuff. And so now we can actually differentiate this. So remember, we're differentiating it implicitly and with respect to time. So deriving v, we will get dv dt. That equals, all of this is just a constant, and it's multiplied by h cubed. So we just bring all of this constant stuff down. So pi over 3 times 3 over 2 all squared. And then we derive h cubed, and deriving h cubed implicitly, that is going to give us 3h squared. But don't forget, we have to multiply by the derivative of h, so that will be times dh dt. And now that we have this all derived, what we could do is we could plug in all of our stuff here that we have the information for. So we're finding dv dt, so dv dt is the only thing we leave as it is. And that equals pi over 3 times 3 over 2 all squared times 3 times h squared, so h will have to plug in a value, and then times dh dt, so we'll have to plug in a value for that. H right here we have written as that is equal to 12, and then dh dt equals 0.045. And it's at this point you just throw all of this mess into your calculator, and then doing that, so let me check the answer, and if we plug all that in, we will get that dv dt equals, where is it? 45.804, and that's our number value. But for related rates, what we always want to do is include units in the final answer. And so this is the rate of change of volume, so that's going to be units cubed. And we were working with, it's here we say feet per minute, so that means we're going to be feet cubed, cubic feet, I believe. Yes. Yeah, cubic feet per minute. And that is our answer. Okay, so now we're going to look at a few shadow problems. Before we start, I'm going to tell you now that the way we solve shadow problems is, for our equation, we're going to use similar triangles to find our equation we differentiate and plug values into. So let's hop right into it. A 7-foot tall person is walking away from a 20-foot tall lamppost at a rate of 5 feet per second. At what rate is a person's shadow changing when they are 16 feet from the lamppost? So let's go back, get some information, start drawing a picture. We have a 7-foot tall person. So let's just draw our guy right here. And he is 7 feet tall. And he's walking away from a 20-foot tall lamppost. So if this was our lamppost right here, and that's 20 feet tall, let's make sure we draw our ground. He's walking away. And it says that he's walking away at a rate of 5 feet per second. So he's walking away, and we don't have any like good variable names here, like no v for velocity, no a for area or anything like that. And so as I said before, when we don't have a good variable, let's just choose a simple letter. And we're actually not using x or y at the moment, so let's just use those letters. So we could say he's saying that. Let me rephrase that. It says he's walking away at a rate of 5 feet per second. So let's just say dx dt is that rate. And let's say dx dt equals 5. Now, where do we actually want to place x on our picture here? Well, he's walking away at 5 feet per second, so this would be our x, because this is the value that's increasing at 5 feet per second. Now, if we could continue on, it says at what rate? So we're finding a rate, the rate of his shadow changing when he is 16 feet from the lamppost. So that means when x is 15, because this value is going to be 16. So when x is 16, we want to find, and then d what dt? We don't have an actual value for that yet. But if we look, the light's going to cast a shadow, or cast down like this, so his shadow is going to be this value. So everything between where the light ends and after the guy. So we're going to have to create another variable right here. We don't have a good variable name, so let's just call this y. And so because we want to find the rate of change of the shadow length, we're going to call this to find dy dt is what we're solving for in this problem. So, continuing this, so we actually have a really good picture here, and I said we're talking about similar triangles. So let's see if we could find any similar triangles in all this. And the thing we notice is this whole giant section here. This is all one big triangle. So that is our first triangle. So let's just write like a fraction representing this triangle. So x plus y is the base of the triangle. And then we're going to write that over the height of the triangle, which is 20. And that's going to equal a triangle that's similar to it. But what do we have? What's a similar triangle in this situation? And the one that we see here is actually going to be this triangle right here. So the large triangle is from the lamppost to the end of the guy's shadow that whole time. But the smaller triangle is between the guy himself and his shadow. So the smaller triangle, the actual sides and stuff, so the base is just going to be y. And the height is going to be 7, because the guy's 7 feet tall. I know the triangle I drew intersects through his head, but whatever. But this is just, he's 7 feet tall, so the height is 7. And now we actually have an equation. X plus y over 20 equals y over 7. Excuse me. So what we want to do here, we could differentiate this right now, but it doesn't look the prettiest. So what we could do is we could just cross multiply, start simplifying things. So over here we will get 7x plus 7y equals 20y. And then we get subtract 7y on both sides. That'll give us 7x equals 13y. So let's write this over here so we have more room. 7x equals 13y. And then let's just differentiate this. Remember, the related rates, so respect to time. So this will turn into 7 dx dt equals 13 dy dt. And if we go back to our provided information, we have dx dt equals 5, and we're finding dy dt. So 7 times 5 equals 13 dy dt. And that means dy dt is equal to 35 over 13. And remember, we need units, and over here it's saying that it's the rate of change of the shadow, and everything is in feet, so and then it's also in seconds. So it's going to be 13 over 35 feet per second. And that's all you really need to do for this kind of shadow problem. And an important thing to notice that shadow problems actually teach us is we don't necessarily always use all our information. Because remember, we were told x equals 16. We never used that. But that's just something, we never used x equals 16. So you don't always use all your information, but you should always consider it at the very least. Okay, so now we're going to give an example of a Pythagorean theorem problem. So this one actually gives us a lot of information just right off the bat. It says that the sides of the given rectangle increase such that dz dt equals 1 and dx dt will equal 3 times dy dt. Find dx dt at the instant x equals 4 and y equals 3. So to solve this, we're not actually given an equation, but here's a hint. It says it's a Pythagorean theorem problem, is what I told you about. So we're probably going to use the Pythagorean theorem. X squared plus y squared equals z squared. I know we typically use a squared plus b squared is c squared, but we're given x, y, and z. So let's go through and highlight our information and start writing stuff down. So it says the increase, so dz dt equals 1. That's important. And dx dt equals 3 dy dt. Now let's rewrite this just in case we want it the other way later. That's the same as saying 1/3 dx dt is equal to dy dt. And lastly, it says find dx dt. So find dx dt when x equals 4 and y equals 3. So let's move back to our actual equation we have here, and let's take the derivative of the Pythagorean theorem. Implicitly, of course, so it's going to be 2x times dx dt plus 2y times dy dt equals 2z dz dt. Remember, whenever you have z's in these problems, write that slash through the z so that we can actually read it or whatever. And speaking of read it, I see that this is in the light, so I'm just going to rewrite the board real quick so this is not in the middle of the light. Okay, this should be better for you guys to see it. Just got all our information on the left side here, and then our actual derivative work here. So it was x squared plus y squared equals z squared. Deriving that, we get 2x dx dt plus 2y dy dt equals 2z dz dt. And a nice thing we could do right here, they all have a 2, so we could just get rid of the 2. Remember, if we're actually showing work for an actual problem, like on a test, make sure you write the 2 and then cancel it later. Don't just erase it like I did, but just for example purposes, we could get rid of it. So now, what we want to do is we plug in our values, and it said we are solving for dx dt. So dx dt is what we're going to leave as it is. So we want values for everything else. So I'm just going to write blank spaces here. We actually go plug stuff in. So we were told x equals 4. So that's x is 4, y is 3. We were told that dz dt equals 1. But now we have 2 extra blanks for dy dt and for z. Now let's start with z because z is easiest. So we're working with a right triangle, as we can see up here, and they say that x equals 4 and y equals 3. So we could just do Pythagorean theorem to solve this, but remember, 3, 4, and then another number is a Pythagorean triplet. It's 3, 4, 5. So if you just remember 3, 4, 5 right triangle, then you could just solve this one pretty much immediately. So for z, our answer is going to be 5. Let's get rid of that. Now dy dt. This is we were told dx dt equals 3 dy dt. But remember, I also had to solve for dy dt just in case we needed it. So dy dt equals 1/3 dx dt. And that is what we're going to plug into here. So instead of dy dt, we write 1/3 dx dt. Now let's simplify this a bit. So 4 dx dt plus 3 times 1/3 dx dt is the same as plus 1 dx dt. And that's going to equal 5. 4 dx dt plus 1 dx dt is 5 dx dt. That's equal to 5. 5 by 5 on both sides. We just get that dx dt is equal to 1. And in this case, we don't have any units, so we could just leave it just like that. And now lastly, our last kind of problem is with trig. So this one says, a missile is fired vertically from a point that is 5 miles from a tracking station at the same elevation. And the angle of elevation, theta, is determined to change at a rate of 0.035 radians per second. Find the rate of change of height when the angle is pi/6. And we are given this picture. So let's go through again and highlight some stuff, get some information. So it says missiles fired vertically from a point that's 5 miles from the tracking station. And that's actually given to us in the picture. The angle of elevation, theta, is determined to change at a rate of 0.035 radians per second. So we're told that it's of theta and the rate of change of theta, so that's going to be d theta dt. We're told that equals 0.035. And now we want to find the rate of change of the height. So the rate of change of the height is going to be this value. This value is the height. And so we want to find the rate of change of height. So find dh dt. And then we want to do that when the angle is pi/6. So that means when theta equals pi/6. So we're just going to go with this as it's a right triangle. And that's how we kind of solve these problems. We treat it as a right triangle. And then we use a trig function to actually solve. So we were given h, or we're working with h, and we were given that this is 5. So this, in respect to theta, this is the opposite, and this is the adjacent. So we're going to use tangent. So we're going to write the equation, tangent of theta. That's going to equal h over 5. And so now what we do is we just differentiate like normal. So that means secant squared of theta times d theta dt is equal. Now don't just think it, don't do quotient rule with h over 5. Treat it as 1/5 h. And so that will give us 1/5 dh dt. And now we could actually just plug in values. So, or we can plug in values, but the first thing I'm going to do is just move secant squared to the other side. Secant squared is the same as 1 over cosine squared. So let's just multiply both sides by cosine squared. So that will give us d theta dt equals cosine squared of theta times 1/5 times dh dt. Now let's plug in our values. D theta dt is equal to cosine squared of pi/6, because theta is pi/6, all multiplied by 1/5 and multiplied by dh dt. But dh dt is what we're trying to solve. So d theta dt actually we need a value for. I kind of got mixed up in my head what we're solving for. So let's plug in 0.035 for d theta dt. And so I guess I kind of moved this cosine thing to the other side for no reason because I wasn't thinking, but it's still going to work out. Cosines of pi over 6. Pi over 6 is down here on the unit circle, and that is going to be root 3 over 2. So we're going to have root 3 over 2 all squared. And then we still have this 0.035 on the other side. And then we didn't change that 1/5, and we didn't change that dh dt. So now let's just divide both sides by these constants. So 0.035 divided by all this crap is going to equal dh dt. And you just plug that into your calculator because it's related rates, it's calculator active. And that is going to give us that dh dt is equal to 0.233. And now we need our units. We're talking about miles, and says that it's changing at per second, so this is going to be miles per second. And that is our answer. Okay, now to wrap up, I'm going to go through a 3-part question that reviews a couple, not all, but a couple of the different kinds of related rates, and then we're just going to be finished from there. So this one says a ladder that is 25 feet long is leaning on a house. The base of the ladder is pulled away from the wall at 2 feet per second. So before I read part A, I'm just going to help start to draw a picture of this scenario. So we have our wall on our floor, and the ladder is leaning against the wall like this. The ladder is 25 feet long. And because 25 feet long ladder, that's constant, not changing, I can write 25 as the length of the ladder, and I don't have to put a variable there because it's constant, not changing. Now, it says that the base of the ladder is pulled away at a rate of 2 feet per second. So we're going to need, this is like the base of the ladder right here. Bottom is the base. So we're going to need a variable to show the rate of change for right here. And because it's the ground, we could just say, let's probably just do a G. G for ground. And then it says that is being at a rate of 2 feet per second. That was English. It's being pulled away at a rate of 2 feet per second. So that means dg dt is going to equal 2. Now, that's all we were told in the base problem. So let's keep going and read question A. How fast is the top of the ladder moving down the wall when the base of the ladder is 15 feet from the wall? 15 feet from the wall. So that is when G is 15. So in this problem, we want to find, so how fast is the top of the ladder moving down the wall? That's what they're asking for. And it's kind of subtly asking for a rate. So it's subtly asking for the rate of how this length is changing. So we're going to have to give this length a variable. And this is the wall, so let's just call this W. And so for part A, they want us to find dw dt. And they want us to do this when G is equal to 15, as we highlighted earlier. So we don't actually have like a great equation here, but this is a wall on a floor, and that's a right triangle. And so because there's a right triangle, and we have kind of values for W and G, or at least some of them, let's do a Pythagorean theorem kind of problem with this. That's what it looks like it is. So W squared plus G squared equals 25 squared. And now let's take the derivative of this. 2W dw dt plus 2G dg dt equals, now 25 squared is a constant, so that's just going to be 0 after we derive it. And now we're going to have to actually plug in values. We want to find dw dt, so dw dt is going to stay there. The other thing we could do is we could cancel these 2's like we did with the last time. But now we plug in our values. So we need a value for W, we need a value for G, and a value for dg dt. dg dt we were told is 2. And G we were told is 15. But we weren't specifically told a value for W. But like with our last Pythagorean theorem problem, we can actually solve for that with the Pythagorean theorem itself. So the hypotenuse is 25 and G is 15. So we need a value for right here. And this just looks like Pythagorean theorem itself, but this is also a Pythagorean triplet. This is sneakily, very sneakily, a 3, 4, 5, because 25 is the same as 5 times 5, and 15 is the same as 3 times 5. So this is a 3, 4, 5, but everything is multiplied by 5. So this side is just going to be 4 times 5, which is equal to 20. So that means W in this situation is equal to 20. So 20 dw dt equals 15 times 2, which is 30. Or no, it doesn't equal 30. Plus 30 equals 0. My bad, I got the signs wrong because I forgot to write equals 0 over here. So let's subtract 30 over, so 20 dw dt equals negative 30. And that means dw dt equals a negative 1.5. And in terms of units for all this, this is feet per second, so negative 1.5 feet per second. And now we can move on to part B. Okay, so part B asks us, consider the triangle made by the ladder, the floor, and the wall, or the house, whatever. Find the rate of change of the area of the triangle, find the rate of change that the area of the triangle, whatever, is when the ladder is 15 feet from the wall. So we're trying to find the change of the area of the triangle when the ladder is 15. And so ladder is 15, that was the same as last question, so G is going to be 15. And remember, based off of last question solving with that means W is equal to 20. So keep that in mind. We want to find the rate of change of the area of the triangle. And so area, typically, we use an A. So dA dt. I typically use a capital A when we're talking about area. So we want to find dA dt. Now we're not given an equation here, but we're talking about area of a triangle. And if you remember, area of a triangle is base times height over 2. But if we write this in terms of our variables, it's going to equal G times W over 2. And that is going to be what area is. So now if we take the derivative of this, we have dA dt equals, let's just factor out that 1/2 as that, and then we have product rule with G and H. So that's going to give us dG dt times W plus dW dt times G. And now we could plug in values that we have for all this, and G is 15, or dA dt. Let me write the blanks first before we actually start plugging stuff in. So we wanted to find dA dt, so we're going to have a blank here, plus blank here times a blank here. G is 15, so let's plug that in first. Sorry. W is 20. And dG dt and dW dt. We were told in the start of the problem dG dt is 2. And we just found dW dt in our last answer for part A, and that was negative 1.5. So now we just gotta basically plug this into our calculator again with all of this stuff. And let me check the answer of that one for you guys. And that is going to be about 8.75. And now we gotta find our units. So this is a rate of change of area, and everything's in feet. So this is gonna be feet squared, and then it's in seconds. So 8.75 feet squared per second. And that is part B. Okay, part C. So part C wants us to find the rate of the angle between the ladder and wall, find the rate of that changing when the base of the ladder is 15 feet from the wall. Let's highlight that again, even though it's basically the same thing that we've been using this whole time. So again, G is equal to 15, and that means W is equal to 20. And also in the top there, we had that dG dt is equal to 2. So the angle between the ladder and the wall, so that's going to be this angle right up here in the top. So this looks like, because we have theta, it's going to be another one of those trig ones. And an important thing here, we do have a value for W, but we solve for that value for W. So if possible, you want to use, for these trig ones, values that were provided to you. And just in case you got something wrong when we were solving for this, maybe this wasn't 20 or something. Like maybe we wrote 21 and we went with the whole problem. If we were to do that same thing, like trig with W and G, we could get it wrong because we calculated W. But if we did the trig related rates with the provided values, which are G and 25, then we would have a higher chance of getting the answer right. So we're going to use a trig function that involves G and 25, as those are the two values provided to us. And in respect to theta, that's going to be the opposite in hypotenuse, so we're going to use sine. So sine of, sine of theta equals G over 25, because opposite over hypotenuse. Now let's take the derivative of that. That's going to be cosine of theta times d theta dt. And that's going to equal, remember, treat this as 1 over 25g. So it's going to be 1 over 25 dg dt. Now, plugging in values, we're looking for the rate of change of angle. So that means we want to find d theta dt. So let's move everything other than d theta dt to the other side first. So that's going to be 1 over 25 times dg dt times 1 over cosine of theta. Now, if we start plugging stuff in, 1 over 25, that's the same. We were told dg dt equals 2. But what about that 1 over cosine theta? We don't have a value for theta, but we don't actually need it. We just need to know what cosine of theta is. And so cosine of theta is going to be w over 25. So I guess in this case, it didn't really matter if we chose w and g, because we're going to use w anyway. But it's just a safe practice. Use values provided to you when you can. So we discovered, or through calculating, that w is 20. So cosine of theta is going to be 20 over 25. So over here, this is 1 over cosine theta. So that's 1 over 20 over 25. So that's the same as 25 over 20. If we look at these 25's cancel, and this 2 cancels with the 20 to make it 10 in the denominator. So d theta dt is going to equal 1/10. And in terms of units, when we're working with theta, this is going to be radians. And in terms of time here, we're working with seconds, so it's 1 over 10 radians per second. And that is our final answer. And that is basically my overview of review for related rates.